Hello, ma'am. Hello. Hello, ma'am. Can you hear me?
Yes, sir. Yes, sir. You can start, sir.
It's
Good evening,
raining
sir.
very badly.
Good evening, sir.
Ma'am,
You can start, sir.
make me a host, ma'am.
Yes, sir. Yes, sir. Done, sir.
Yes. Good evening, students.
Good evening, sir.
Yeah. There is a heavy downpour here. Rains heavy. I don't know about the internet stability. We have to adjust. Yes, we will start and we'll do our work. Colligative properties of electrolytes. We've been learning colligative properties in this chapter. The last part of the topic, Van 't Hoff factor, we are supposed to learn. Before we get into the topic Van 't Hoff factor, we will try to summarize the colligative properties what you've learned. So colligative properties of a solution, namely lowering of vapor pressure, osmotic pressure, elevation in boiling point, depression in freezing point. These are the four colligative properties what we have learned. All this colligative property depends on the number of solute particles, and they do not depend on the nature. They depend only on the number of solute particles, not on the nature of the solute particles. Now, since electrolytes ionize, now just see the difference what we're talking about. Now, in case of colligative properties, what we learned, we used molecules which do not dissociate or associate. So the condition for us to learning the colligative properties is the solute should not dissociate or associate, meaning the solution should not undergo ionization to form Na plus or Cl minus, or associate means molecules should not join with each other to form a dimer. Now, for an example, if I take this molecule CH3, C double bond O, OH, what's the name of this molecule?
Sir, acetic acid.
Acetic acid, very good. What's the name of this molecule? C, OH, and double bond. What is this? This is also what?
Acetic acid, sir.
When acetic acid is dissolved in water, what happens is these acetic acid molecules will join with each other through a hydrogen bonding. So this kind of molecules are called as dimer. What do you mean by dimer? Di means two, mer means molecules. So this kind of process is called as association. Now, if you take NaCl, it will dissociate to form Na plus and Cl minus. This process is called as dissociation. Breaking of a molecule into ions is called as dissociation. But association is combining of two molecules to form a dimer is called as association. Now, if you take glucose is C6H12O6. When this glucose is dissolved in water, it remains as C6H12O6. That means glucose will not undergo dissociation nor association. The glucose molecule will remain same. These are called as non-electrolyte. Molecule which does not undergo dissociation will be called as non-electrolyte. Now, in case of the colligative property, studying lowering of vapor pressure, osmotic pressure, elevation in boiling point, and depression in freezing point, we studied their properties using non-electrolyte. That means like glucose we've used. You have used urea, NH2CO, NH2 urea. So all these molecules will not undergo what? A dissociation. For those kind of molecules only, we have learned the colligative properties. But now we have to extend this colligative property studies for electrolytes. Now, since electrolytes ionize to give more than one particle per formula unit in the solution. What do you mean by per formula unit in a solution? See, if the formula unit is NaCl, this is one molecule, NaCl. But when water is two particles, one is sodium ion, the second one is what? Chloride ion. So therefore, it gives more than one particles. Those are called as what? Electrolytes. The colligative effect of an electrolyte solution is always greater than that of non-electrolyte of the same molar concentration. So for a solution which undergoes dissociation, the colligative effect of the electrolyte solution is always greater than that of non-electrolyte of the same molar concentration. So if you take 1 molar HCl and 1 molar glucose, the colligative property of NaCl will be more compared to the colligative effect, not the property. Effect will be more for NaCl because it gives double the particles, but glucose does not dissociate. That is what it means. All colligative properties are used to calculate molecular mass. If you remember the colligative properties, what we learned in the previous classes, all these colligative properties were used to find the molecular mass of the solute. And especially it is for non-volatile solutes. You know what is volatile, which vaporizes. Those are called as volatile, non-volatile solutes. Glucose is a non-volatile solute. Urea is a non-volatile solute. However, osmotic pressure is the best colligative property for determining molecular mass of volatile substance. So amongst the 4 colligative property, osmotic pressure is the best colligative property to determine the molecular mass. Remember, this is important. Maybe they can ask you amongst the colligative property, which is the best colligative property. So it is osmotic pressure to determine the molecular mass. Now, some of the properties we will learn. Colligative properties are depending on the following factors, not why, it is factors. The first one is colligative property is directly proportional to number of particles. Colligative property is directly proportional to number of particles. We learned it today also. Colligative property depends only on the number of solute particles, not on the nature. So colligative property is directly proportional to number of particles. Now, when I say directly proportional to number of particles, in case of non-electrolytes, it is directly proportional to molecules. Now, for example, glucose. Glucose is a non-electrolyte. Urea is a non-electrolyte. So it directly depends on the number of glucose molecules and molecules. In case of electrolyte like sodium chloride, which will dissociate to form Na plus and Cl minus, it's directly proportional to number of ions. It's directly proportional to number of ions, Na plus and Cl minus. So likewise, colligative property is directly proportional to number of moles of solute, and it's also directly proportional to mole fraction of the solute. So this mole fraction of the solute we learned, relative lowering of vapor pressure, a lowering of vapor pressure we learned. So colligative property is directly proportional to molecules. In case of non-electrolyte, it's directly proportional to ions in case of electrolytes, and it's directly proportional to moles, number of moles of solute, and it's also directly proportional to mole fraction of solute. Now we have learned, just remember, we have learned delta F is directly proportional to Kf and M we have learned. Number of moles is nothing but molality, concentration. So mole fraction we have learned relative lowering of vapor pressure P0 minus P divided by P0 is equal to N2 divided by N1 plus N2. So that is what this mole fraction stands for, and this is what number of moles stands for. I hope you're following.
Yes, sir.
Yes. Now, the first property is factor is colligative property is directly proportional to number of particles. The second factor, for different solutes of same molar concentration, the magnitude of the colligative property is more for that solution, which gives more number of particles on ionization. Meaning, if I take NaCl, you get Na plus and Cl minus. If we take electrolyte calcium chloride, if you take, assuming it undergoes complete dissociation, it's calcium ions and 2 chloride ions. See, in this case, it is only 2 ions, but in this case, it is 3 ions. Therefore, what they say is, for a different solution of same molar concentration, I take 1 molar HCl and also I take 1 molar calcium chloride. The magnitude of the colligative property is more for that solution, which gives more number of particles on ionization. That means the magnitude of the colligative property will be more for calcium chloride compared to sodium chloride. Because calcium chloride gives you how many ions? 3 ions. Sodium chloride gives only 2 ions. Therefore, colligative property this magnitude of the colligative property will be more for calcium chloride. The second point. The third point, for different solutions of same molar concentration of different non-electrolyte solution, the magnitude of the colligative property will be same for all. For different solution of same molar concentration of different non-electrolytes, that is 1 molar glucose you can take, 1 molar urea you can take. These are different non-electrolytes, but the concentration is same. When the concentration is same, the colligative property, the magnitude of the colligative property will be what? Same. The magnitude of colligative property will remain same. Are you with me? Are you following?
Yes, sir.
Yeah. For different molar concentration of the same solute, the magnitude of the colligative property is more for more concentrated solution. Meaning, if I take 1 molar glucose and if I take 0.5 molar glucose, now here the number of molecules is more in 1 molar glucose. Therefore, the magnitude of 1 molar of glucose will be more compared to 0.5 molar glucose. For different molar concentration of same solute, the magnitude of the colligative property is more for more concentrated solution. The fifth point, for solutions of different solutes, but of same percent strength, the magnitude of colligative property is more for the solute with less molecular mass. For a solution of different solutes, but same percent strength. Same percent strength means same concentration. Different solute, same percent strength, weight percent strength. The magnitude of colligative property is more for the solute with least molecular mass. When we have least molecular mass, the number of molecules for same weight will be what? Higher. Therefore, they say the solution of different solutes, but of same percent strength, the magnitude of colligative property is more for the solute with least molecular mass, molecular weight. Sixth one, for solution of different solutes of same percent strength, the magnitude of colligative property is more for the solute, which gives more number of particles. We have learned in the first point, colligative property is directly proportional to number of particles. The same thing, which can be known by the knowledge of molecular weight and ionization behavior. We have learned it in the first factor. So this is with respect to colligative properties, the factors affecting colligative property. Now we have to learn an important concept, the last part of the concept, that's called as abnormal molecular mass. Abnormal molecular mass. What is this abnormal molecular mass? I briefly tell you. If we take NaCl, atomic mass of sodium is 23, chlorine is 35.5. Therefore, the molecular mass is 58.5. This is the theoretical molecular weight. This is the theoretical molecular weight. We just calculated based on the atomic mass of it. Now, the same sodium chloride, if we take sodium chloride and find the molecular mass experimentally, if you see the molecular mass or determine the molecular mass, experimental molecular weight of sodium chloride will be 29.25. Experimental molecular mass will be 29.25. Why this is 29.25, we will learn. Theoretically, it is 58.5, but experimentally it is 29.25. Now, for acetic acid, the molecular mass, theoretical molecular mass is 60, but experimental molecular mass will be 120. So that means components are showing what? Different molecular mass. That is why we call it as what? Abnormal molecular mass. Why this difference in molecular mass, experimental molecular mass, we will learn. Molecular mass can be calculated by measuring any of the colligative property. What do you mean by any of the colligative property? We can either use osmotic pressure, elevation in boiling point, depression in freezing point, or what? The lowering of vapor pressure. Any of the property can be used. The relation between colligative properties and molecular mass of the solute is based on the following assumption. The relation between colligative property and molecular mass of the solute is based on the following assumption. First one, the solution is dilute, so that Raoult's law is obeyed. So we all learn colligative property or solutions chapter only for dilute solution. That's the first criteria. The solute neither undergoes dissociation nor association in the solution. So the solute should not undergo dissociation nor association. But you see here, in case of acetic acid, I taught you in the beginning of the class, it undergoes association, forming dimer, I told you. Here, NaCl undergoes dissociation, I told you, to form Na plus and Cl minus. But what is the criteria? The solution should be dilute first, and the solute should not undergo dissociation or association. In the case of solutions where above assumption not valid, we find discrepancies. That means in case of acetic acid, in case of NaCl, which it will not obey Raoult's law because this NaCl is undergoing dissociation and acetic acid is undergoing association. Therefore, there is a difference in molecular mass. And that process that is termed as discrepancies between observed and calculated values of colligative properties. These anomalies are primarily due to association of the solute or dissociation of the solute. So abnormal molecular mass is because of two reasons. One is due to association of the solute. If the solute particle gets associated, it will show abnormal molecular mass. Or if the solute gets dissociated, then also the solute will show abnormal molecular mass. A very important concept we'll be learning, and we'll be learning some of the questions also based on this. Now, association of solute molecules. Association of solute molecules. Certain solute in the solution found to associate. This eventually leads to decrease in number of molecular particles in the solution. Assuming 100 acetic acid molecule, 100 acetic acid molecule is put in water. Now, when 100 acetic acid molecule is put in water, these 100 acetic molecules will undergo association. So dimers are formed. So in water, how many molecules will be there? How many molecules will be there? Only how many particles will be there? Not molecules. How many particles will be there? Only 50. Are you getting this point? Students, are you following?
Yes, sir.
Students,
Yes, sir.
others, did you follow?
Yes, sir.
Yeah, see, and I told you acetic acid undergoes association. Two acetic acid molecule undergoes association to form one dimer. If I have 100 molecules of acetic acid, so therefore how many dimers will be formed? 50. So that means in solution, we have only 50 particles. So here eventually leads to decrease in the number of particles for components which undergoes association. Thus, it results in the decrease in the value of colligative property. Thus, it results in the decrease of colligative property. So, colligative property is inversely proportional to molecular mass of the solute. Colligative property is inversely proportional to molecular mass of the solute. Therefore, higher values are obtained for molecular mass than normal molecular mass for unassociated molecules. So, higher values are obtained for molecular mass than normal molecules, than normal values for unassociated molecules. Unassociated molecules, but here it's associated. I'll give you the formula later in this class and we'll work out some problems. Dissociation of solute. A number of electrolytes dissociates in solution to give two or more particles, ions. Therefore, the number of solute particles in the solution of the substance is more than expected. That means if I take 10 molecules of NaCl and put it in water, I'll get to a 10 Na plus and I'll get 10 Cl minus 10. Therefore, totally how many particles will be there? 20 particles. How many particles we have taken? 10, but in solution it will be what? 20. Double. Now, if I take aluminum chloride, if I take 10 molecules, you will have aluminum 3 plus and 3 Cl minus. So this will give you 10 and this will give you 30. So totally 40 molecules. Are you following what I'm saying? 40 particles. So for an electrolyte which dissociates to give two or more particles, therefore the number of solute particles in solution of substance is more than expected value. Here expected is 10, but what's observed? 40. Here expected is 10, here what you observed? 20. Likewise. Accordingly, such a solution exhibits higher values of colligative property. So accordingly, such a solution exhibits higher value of colligative property. Since colligative properties are inversely proportional to molecular mass, therefore, molecular mass of the subsubstance are calculated from colligative property values will be less than their normal values. Since colligative property is inversely proportional to molecular mass, for such substances are calculated from colligative properties will be less than their normal values. Van 't Hoff is the name of a person. Van 't Hoff factor is represented by letter I. In 1886, Van 't Hoff introduced a factor I called as Van 't Hoff factor to express the extent of association or dissociation of the solute in the solution. It is the ratio of normal and observed molecular mass of the solute. See, normal, what is Van 't Hoff factor I? Normal molecular mass by observed molecular mass. What do you mean by normal molecular mass? Theoretical molecular mass by experimental molecular mass or molecular weight, whatever it is. So normal molecular means theoretical molecular mass, observed molecular means experimental molecular mass. In case of association, observed molecular mass being more than normal, the factor I has a value less than 1. So if Van 't Hoff factor I is less than 1, then we understand that the solute undergoes dissociation. The solute undergoes dissociation. Now the conclusion is, see this, observed molecular mass being more than normal, the factor I has a value less than 1. Now if you remember, acetic acid, I told you, acetic acid, theoretical molecular mass is 60 Ig. And experimental molecular mass, I told you it is 120. Now just observe. Now in case of what is it? In case of association, so it should be like this, experimental molecular mass. There's something wrong. Experimental molecular mass by theoretical molecular mass. Theoretical molecular mass, EMW divided by TMW, because it says greater than 1. No, Van 't Hoff factor is less than 1. No, then it's correct only, man. What you've done is correct. Sorry, less than 1. So I made a mistake. I was thinking something. Theoretical molecular mass by experimental molecular mass. Now, theoretical molecular mass is 60 for acetic acid. Experimental molecular mass is 120. That means the ratio is what? 0.5. So that means it is less than 1. When it's less than 1, it undergoes association. It undergoes association. Observed molecular mass being more than normal, the Van 't Hoff factor I as a value less than 1. See, it's association. I don't know why I wrote dissociation. So if I is less than 1, Van 't Hoff factor is less than 1, the component will undergo association. Now, for an example, I told you for sodium chloride, the theoretical molecular mass is 58.5, and experimental molecular mass, I told you it's 29.5. Now, as per the understanding, what is I? Theoretical molecular mass by experimental molecular mass. That is 58.5 divided by 29.25 in specific, it's almost equal to 2. That means if I is greater than 1, the solute undergoes dissociation. The solute undergoes dissociation. Are you getting this point?
Yes, sir.
Yes. Now just observe. I take glucose. In case of glucose, theoretical molecular mass is 180. Experimental molecular mass is also 180. So what will be Van 't Hoff factor? It will be 180 divided by 180. It will be 1. So when Van 't Hoff factor is 1, the solute undergoes no dissociation, nor the solute undergoes association. So 3 terms we learned. What is that 3 terms learned? When I is less than 1, the solute undergoes association. When I is greater than 1, the solute undergoes dissociation. And when I is equal to 1, no dissociation or association. No dissociation or association. Did you understand this?
Yes, sir.
Yes. Now you see this a different way of representing. I is observed value of colligative property divided by calculated value of colligative property, assuming no dissociation or association. I number of particles after association or dissociation divided by total number of particles before association or dissociation. There are ways to calculate what? Van 't Hoff factor. Now, if you take NaCl, in case of NaCl, before dissociation, it is 1. After dissociation, it is how much? After dissociation, how much? 1 plus 1, it is 2. So it will be 1 divided by 2, again it's 0.5. See here. Where's that 0.5 for NaCl? Not 2 by 5. 2 by 1, sorry, 2 by 1, it is again 2. Here we learned 2. So either way, the answer will remain same. So any one of the formula can be used. The equation of the colligative property. So light undergoes dissociation or association, the Van 't Hoff, the equations of the colligative property is what? Modified. Now, what's the modification we are going to learn now? Now, 2 equations I will give you. You have to remember this 2 equations to work out the problems. For a solute which undergoes association, Van 't Hoff factor I is given by the formula, or maybe we can say degree of association, not Van 't Hoff factor, degree of association. We will write like this: degree of association is represented by letter alpha. It's given by the formula I minus 1 divided by n minus 1. What is I? I is called as Van 't Hoff factor. N is number of particles. So this is the formula to calculate degree of association. Likewise, degree of dissociation is also represented by letter alpha, and it is given by the formula. It is I minus 1 divided by 1 divided by n minus 1. 1 divided by n minus 1. This is the formula to calculate the Van 't Hoff factor for a solution which undergoes, not Van 't Hoff factor, degree of dissociation, alpha. Degree of dissociation alpha is given by the formula I minus 1 divided by 1 by n minus 1. N is number of particles and I stands for Van 't Hoff factor. Van 't Hoff factor. We will try to learn some of the questions so that it will be easy for you to understand. Now, the first question is the Van 't Hoff factor I for a dilute aqueous solution of strong electrolyte barium hydroxide. Barium hydroxide. Barium hydroxide is BaOH twice. Now, the strong electrolyte, they say, when we say strong electrolyte, they undergo complete dissociation. They undergo complete dissociation, Ba2 plus 2OH minus. So for these kind, Van 't Hoff factor is equal to total number of ions. Total number of ions after dissociation. Total number of ions after dissociation. What's the total number of ions? 1 plus 2. So Van 't Hoff factor I will be 3. Van 't Hoff factor I will be 3. So the answer for this question is option D. So number of ions is what? 1 plus 2. Therefore, it is 3. Van 't Hoff factor will be 3. Did you follow? Van 't Hoff factor I for a dilute aqueous solution of a strong electrolyte like barium hydroxide. When we say strong electrolyte, remember it undergoes complete dissociation. So 1 molecule of barium hydroxide gives you 1 barium ion and 2 hydroxyl ions. Therefore, the total number of ions is 3. Hence, Van 't Hoff factor is equal to 3. Did you understand the simple problem?
Yes, sir.
Yes, sir.
Now, this is easy, but let's try to understand. Which one of the following electrolyte has same Van 't Hoff factor I as that of aluminum sulfate? If all are 100% ionized, all are 100% ionized means potassium sulfate. Now, this potassium sulfate will dissociate to form 2K plus and 1 SO4 2 minus. It gives how many ions? 3 ions. Now, if you take B, K3 FeCN6, it is a complex you will not be knowing this. But I don't know whether you've been taught in school, but anyways, we will understand this. This gives you 3K plus Fe CN6 3 minus. Therefore, it's 3 plus 1, 4 ions. 4 ions. Option 3, AlNO3 thrice, aluminum nitrate. This will dissociate to form Al3 plus 3 moles of NO3 minus. So it is 1 plus 3. It is again giving you 4 ions. The last one, if you see, K4FeCN6. This will dissociate to form 4K plus FeCN6 4 minus. So this gives you 4 plus 1, it gives you 5 ions. Now what they say, which one of the following electrolyte has the same value of Van 't Hoff factor as that of aluminum sulfate? How does aluminum sulfate dissociate? Aluminum sulfate will dissociate to form 2Al3 plus 3 SO4 2 minus. Totally it also gives 2 plus 3, 5 ions. So colligative property depends on number of particles, not on the nature. So aluminum sulfate gives 5 ions and K4FeCN6 also gives 5 ions. Therefore, this and this will have aluminum sulfate and K4FeCN6 will have same colligative property. Hence, the answer for this question will be option D. Did you understand this?
Yes, sir.
The next
Sir,
problem. Yeah, tell me.
So what is the name for K4FeCN6?
Potassium ferrocyanide.
So what about
This will-
B, sir?
This will be called as potassium ferricyanide. Here the ion will have plus 3 charge. Here the ion will have plus 2 charge. When ion has plus 2 charge, it's called as ferro. Here ion has plus 3 charge, therefore it's called as ferri. This is the common name what I gave. IUPAC name for these kind of molecules we will be learning in a chapter called as coordination chemistry. So this is called as potassium ferricyanide and this is called as potassium ferrocyanide. This is a common name. All right.
Okay, sir.
This problem is a lengthier problem, but it's easy. Let's understand. A solution containing 0.52 grams of KCl in 100 ml of water froze at minus 0.25 degrees Celsius. Calculate the percentage ionization of the salt. They are given Kf of water as 1.86 Kelvin per mole. Atomic mass of potassium they have given and chlorine also they have given. Firstly, we will try to calculate the theoretical molecular mass of KCl. It will be 39.1 plus 35.5. That will be equal to 74.6. This is the theoretical molecular mass. Now we will try to, this is based on freezing point. So we will calculate the experimental molecular mass. In order to calculate the experimental molecular mass, it's freezing point. Therefore, it's 1000 into Kf into W divided by small letter w divided by small letter m into capital W. So m will be what now? 1000 into Kf into W divided by delta Tf into capital W. So what is Kf? They've given Kf of water to be 1.86. What is the weight of the solute they've given? 0.52 grams. Divided by, what is the delta Tf? They say they froze at what? Minus 0.25. This minus sign indicates there's a decrease. Do not use minus sign. So what is the decrease? 0.25. So 0.25. And what's the mass of the solvent? They will 100. So it is 100. So on simplifying, we will get 38.688. This is experimental molecular mass. This is experimental molecular mass or observed molecular mass. Now, what is Van 't Hoff factor? It is theoretical molecular mass by experimental molecular mass. Theoretical molecular mass is 74.6. Experimental molecular mass is 38.688. We just now calculated. It's equal to 1.93. So Van 't Hoff factor is equal to 1.93. So if its Van 't Hoff factor is equal to 1.93, and we know that KCl will dissociate to form K plus and Cl minus. How many ions it is giving? It is giving 2 ions. One molecule of KCl gives 2 ions. So if it's giving 2 ions, I will be what? 2. Not I will be 2, N will be 2. So this is undergoing dissociation. So therefore, degree of dissociation is represented by alpha. Degree of dissociation is represented as alpha. Alpha is given by the formula I minus 1 divided by N minus 1. I taught you this formula. I we calculated as 1.93 here. And N we found out to be 2. 2 minus 1. On simplification, we will get 0.93. 0.93. Since the answers are all in percentage, so you have to multiply this by 100. When you multiply this by 100, so you'll get 93%. Therefore, the answer for this question is option A, 93%. Did you follow this problem? It's a lengthy problem. Competitive exams will have very short time to work out these problems. So you should practice more number of problems. Did you understand this?
Yes, sir.
Yes. The next question. These are another few questions are very simple. Directly we will try to answer. Van 't Hoff factor is, this is a question. I don't know what answer to give. Van 't Hoff factor is less than 1 in case of dissociation. More than 1 in case of association. Always less than 1. Less than 1 in case of association. See, this is a straightforward question, correct? In case of acetic acid, what was Van 't Hoff factor? If you remember, it was 0.5. In case of, this is for acetic acid I'm talking. In case of NaCl, what was Van 't Hoff factor? NaCl, sorry. I will be around 2. That means I is greater than 1 when the molecule undergoes dissociation. I is less than 1 if the molecule undergoes association. We were learning. So, see here, in case of association, the Van 't Hoff factor should be less than 1. So, they have, in case of dissociation, Van 't Hoff factor should be greater than 1. But they have said less than 1. This is the wrong option. In case of association, the Van 't Hoff factor should be less than 1, but they have said more than 1. Therefore, this is also wrong. Always less than 1, this is also wrong. So less than 1 in case of association. In case of association, the Van 't Hoff factor should be less than 1. This is the right option. It's option D. Correct?
Yes, sir.
Now the next question is semi-permeable membrane permits passage of, please tell me the answer. Please tell me the answer. Only solvent
Only solvent molecules.
Very good. Only solvent molecules from what? The region of lower concentration
Lower
to
concentration to higher.
region of higher concentration. Therefore, the answer is option A.
Sir, can't hear you, sir.
Huh?
Sir,
What,
can't.
Ajay?
Sir, couldn't hear you, sir.
Now can you hear me?
Sir, it's very feeble, your voice.
It's raining, no man. The internet problem will be there. But I can hear you very clearly. Others can hear, no?
Yes, sir. You are
Yes.
audible.
That means it's a problem with your network, Ajay.
Yes, sir. Let me
Yeah.
check.
Example for solid solution. Please tell me this answer. It's very simple. Example.
bronze.
Huh?
Bronze.
Bronze. Alloys are what? Example for solid solution. Very good. Next, how many moles are represented by 24.5 grams of sulfuric acid? Now, sulfuric acid is very simple. Sulfuric acid, the molecular mass is 1 into 2 plus 32 is the atomic mass of sulfur. Oxygen is 16 into 4. So totally it will be 98. 98 will be the molecular mass of sulfuric acid. So now they're asking number of moles. Number of moles is calculated by the formula weight in grams divided by molecular mass. They have given 24.5 and it is 98 divided by 98. So it will be 0.25 moles. 0.25 moles. Hence the answer for this question is option A, 0.25. This question also, see, there are simple questions. Few more questions we will learn. Which is not a colligative property? Which is not a colligative property?
So vapor pressure.
Very good. Vapor pressure is not a colligative property. All the others are what? Colligative property. This question let us work out. A solution of, what happened? A solution of anhydrous calcium chloride at 0 degrees Celsius developed 15 atmospheric osmotic pressure. 15 atmospheric osmotic pressure. What is the degree of dissociation of calcium chloride? They're asking what is the degree of dissociation of calcium chloride. Read the question. 5% solution of anhydrous calcium chloride. What do you mean by 5% solution of calcium chloride? It means 5 grams of calcium chloride is present in 100 ml, 100 ml, 100 ml. So the molecular mass of calcium chloride, molecular weight of calcium chloride is 111. You can calculate. Calcium is 40, chlorine is 35.5, so it will be 111. So 5 grams is present in 100 ml. So that means 111 grams will be present in what liter? 111 grams will be present in what liter? They're asking. So it should be the calculation. So the calculation is like this, not the cross multiplication. It's not the cross multiplication. So 111 grams of calcium chloride will be present in, the formula is 100 into 111 divided by 5 into 1000. See, 100 gram, in 100 gram, 5 grams is present in 100 ml. So in 1000 ml, what is there? 111 grams. Therefore, what is the amount of calcium carbonate present? That's calcium chloride. It's 100 into 111 divided by 5 to 1000. That is 2.2 liters. 2.22 liters. 2.22 liters. Now we know that this is based on osmotic pressure. We know that pi V is equal to RT. Pi will be what now? RT by V. R is 0.082 and temperature, room temperature, 0 degrees Celsius. It's 273 Kelvin and volume we found it to be 2.22. Therefore, that will be equal to 22.47 divided by 2.22. You will get the answer to be 10.09 atmosphere. 10.09 atmosphere. I don't know whether you understood this part of the problem. If you have not understood this part of the problem, it is nothing but molality, calculation of molality. What's the weight of solvent present in the molality? That's all. So this is 10.98. What is Van 't Hoff factor? Van 't Hoff factor is observed colligative property by experimental or normal colligative property. Normal colligative property. Observed colligative property, what it says in the question, you read the question. 15 atmospheres. The 5% solution of anhydrous calcium chloride at 0 degree developed to 15 atmospheres. This is the observed colligative property, it is 15. Divided by normal colligative property, just now we calculated by the formula, it is 10.09. Therefore, Van 't Hoff factor will be, you can simplify this Van 't Hoff factor. I'm not simplifying directly, we will write what is Van 't Hoff factor, degree of dissociation. Alpha is equal to I minus 1 divided by N minus 1. I is 15 by 10.09 minus 1 divided by N. What is N? Calcium chloride. Calcium chloride gives you how many particles? It will dissociate to form calcium 2 plus and 2Cl minus. So it will be 1 plus 2, it will be 3. So N is 3, 3 minus 1. On simplification, you will get the answer 0.2433. That is 24.33%. 24.33%. Kindly just observe this form question. We'll work out one more problem now. Can we continue with the next problem?
Yes, sir.
Yes. So the next problem, 0.6 ml of glacial acetic acid with a density 1.06 gram per liter is dissolved in 1 kg water, and the solution flows at minus 0.025 degrees Celsius. Calculate the Van Hoff factor, and Kf of water is 1.86 Kelvin kg per mole. See, Van Hoff factor, not Van Hoff factor, Kf is Kelvin kg per mole. You should know the value. What is the volume of glacial acetic acid they've given? Volume of glacial acetic acid is 0.6 ml. Density of acetic acid. Density of acetic acid is 1.06 gram per liter. It's given. Therefore, mass of acetic acid. How do I calculate mass of acetic acid? We know the density is mass by volume. Mass will be what now? Mass of acetic acid will be density into volume. So density is 1.06 and volume is 0.6. That will be equal to 0.636 grams. Did you understand this part? Follow this part?
Yes, sir.
The delta TF will be, what is delta TF? What is delta TF?
So TF naught minus TF.
T naught minus T. Okay, TF naught minus TF. Okay, T naught is 0 degrees minus of minus 0.0205. That will be equal to 0.0205 degrees Celsius, because it's in degrees Celsius. So we'll take it in degrees Celsius itself for now. And in this chapter, degrees Celsius and Kelvin scale, it makes no difference. Anything can be used. Now, what is given otherwise? They've given Kf also. They've given Kf as 1.86 Kelvin kg per mole. Now tell me, what is that we're supposed to find? We're supposed to find Van Hoff factor. So in order to find Van Hoff factor, we know the formula is observed molecular mass divided by theoretical molecular mass. Now, acetic acid is given. Acetic acid, we know the formula of acetic acid. And I told you the molecular mass of acetic acid is 60. Molecular mass of acetic acid is 60. Now, this is the molecular mass. Now, theoretical molecular mass is also calculated by the formula. Theoretical molecular mass is calculated by the formula mass of solute divided by molar mass of solute into mass of solvent. So that will be giving you theoretical molecular mass will be 0.636. We found out here mass of acetic acid solute divided by molecular weight of solute. What's the molecular weight of solute? We just now found it to be 60. And what is the mass of solvent? It is liter, 1 kg water. It's 1 kg. Mass of solvent to be in kgs. So on simplification, we get the value 0.01059. This is the theoretical molecular mass. See, molarity, we also know the formula, molality, or maybe we can write delta TF is equal to KF into what? M, molality. What is molality now? Delta TF by KF. Delta TF we calculated just above. What's the delta TF? It's 0.025. 0.0205. Delta TF. KF, it is 1.86. Therefore, molality is 0.01102. This is the molality. So, Van Hoff factor I is also calculated by, it's a lengthy problem. You should reread once or twice. So, molecular mass, observed molecular mass by theoretical molecular mass. Observed molecular mass is 0.01102. And theoretical molecular mass we calculated here. This is theoretical molecular mass. This is theoretical molecular mass, 0.01059. On simplification, we will get the value 1.041. So the Van Hoff factor of water is 1.041. just go through this problem. It's a long problem and it's confusing. It's a lengthy problem. Unless you know the subject, we cannot work out these kind of problems. Kindly go through. So this chapter comes to an end today. So possibly we will be doing the next chapter, electrochemistry. We will be starting in the next class. So if any clarification, you can get it done now. We have worked more number of problems and all the concepts were discussed here. Yeah, any clarification, please?
No, sir, no doubt.
No? Others? No
No,
doubt?
sir. No doubts.
All right, then we'll meet possibly on, maybe I'll tell you, or madam will tell you, we'll meet. Madam, I'll stop the class, ma'am.
Yes, sir.
Yeah,
Thank you, sir.
Thank you, ma'am.
Thank you, sir.
Yeah, ma'am.
Sir.
Yeah, bye, Ajay. All right.